Hello everyone, it's, oh wait, hold a second. I forgot to do this real fast. Get this one done. Alright. Hello everyone, it's July 15th. Alright, let's do this step by step. Directions from a binary tree node to another. I can guess what the question is. So you're given one node and given another node. Then we want to produce a step-by-step to go from one node to the other. Yeah, you're given a root. Each node is uniquely assigned a value from 1 to n. You're also given integer start value representing the value of the start node, and a different integer destination value representing the destination. Find the shortest path starting from node S and ending at node T. Generate step-by-step directions of such path as a string consisting of only the uppercase letter L and R and U. So U probably goes to parent. Okay, return. Okay, so it's the shortest path, so it's going to be a breadth first search. And as we go through the breadth first search, but hold a second, I just realized one thing. You have to go up, right? We go from 3 to 6, and it's a binary tree. Okay, it's a binary tree, so we can easily find, so we will find the path. Okay, so basically we'll find the path from, we might need something like a lowest common. See, we need this. We need the lowest common ancestor for the two. Now, since we know what they are, so the lowest common ancestor is easy to get. So basically, we start from the root, and we'll search for your start, and then we search for the destination. And as we search through them, we will produce a path. Well, not really a path. Yeah, it would produce a path, right? It would produce a path from the root to the destination. So now we have two paths, right? Then we can go, the two paths, okay, is from the root to one node. Yeah, so basically we'll have the source, we call it start, right? We'll have, root to some n node, to some n2, all the way to start, right? And we also have the destination, which also is from root to n1 prime and 2 prime, all the way to destination. So now we want to know, because the shortest path, so we need to go from the root, just go down to find the, find their lowest common ancestor. So the lowest common ancestor, we can just start from the root. If they're the same, we move forward. What if they're not the same? No, it will be the same, because if we have something the same and go, then all the three will be same. So we go same. So the first one that is different, let's say these are the same, but this is not the same. So we know this is their root. Okay, so now it's going to be n1 to n2, whatever to the start, and n1 to n2 prime to whatever to the destination. So now it will be from the start, which you can trace back this thing, right? We trace back this thing, and all of this is just numbers because every value is unique, right? So we trace back to see how many, basically just a length, right? Which is the length. And like in this case, we'll do 1, 2. So basically the length of this minus 1 will be the number of times you go up. And then from here, we just need to know if it's a left or a right. Okay, so which means when we get there, we have to know if it's a left or right. Okay, so we need a we need an integer array to notify it's a left or right. We can say is left, so it's a 1 or 0, right? 1 or 0. So from here, then we know is this a left or right? Then we get it. Then we follow down this path to add. Oh, okay. Yeah, because you go up, it doesn't really matter. You go up, you just keep going up. Okay, so let's try this. I think we have to GC this thing. Oh, really? We have to do this GC. Okay, so that's the tree node. Okay, so what we need is start value, destination value. What we want is a path, right? We want a path from the root, and then we go through, basically DFS the whole thing, and if we DFS the whole thing, we will get, right, the path, and then we can append to every one, but we only, interested in 2, right? We're only interested in 2, which is the start and the destination. But we need to keep track of all of them, right? Because you go down, and it doesn't fit, so you go down the other one. Is it possible to just, quickly go through the whole thing? Because you have to go the entire, oh my god. Right? You have to go through the entire ones. Yeah, maybe I don't know. Is BFS easier to deal with in this case? No, I do not think so. What I think is we can do like a backtracking to go through the whole thing. Okay, so we need to do a now. How'd you get the value out? You get the value out by, okay, I need to do a int start path. Okay. Oh, I don't even know the length. Well, I don't need to initiate it. All I need to do is dest path, right? That's all I need. And private void DFS. Okay. So we have a tree node, a node, and we need a list integer called a path. Right? Alright, so what we're gonna do is we're gonna add the node, so we say path.add node.val. Well, actually, if node is equal to null, just return. Right? Otherwise, we'll add the node.val, and we say if node.val int start value, int and no dest value. Okay, so if node.val is equal to start.value, or no, we just do that. If it's equal to start.value, then we need to convert. We say, actually we should say this dot, right? Say this dot start path equal to new int path dot size. Okay, Then for int value of path, actually that's not right. Int I 0I smaller than path.size I plus plus. We say start path I equal to path.get I. Okay, so that's that, and we'll copy this entire thing. V this Y, and then paste this, right? And then this is gonna be a destination val, and then this is gonna be dest path, right? This is gonna be dest path. Yep, so we'll do that. Once we finish doing that, we'll say dfs node.left path, dfs node.right path, and once we're done, path.remove path.size -1. Yeah, so it's like backtracking. All right. So we say this dot start value equal to start value, this dot dest value equal to dest value, dest value, dest value. Okay, then we call dfs root path new array list. Okay, so we call this, we have the start path and we have the dest path. Then we're gonna go through them one by one, you know, just to find where the so we can say int lowest common ancestor index equal to 0. Okay, so for while LCA index is smaller than this dot start path dot length, and LCA index smaller than this dot end, also I say end path dot length. If this dot start path LCA index is equal to this dot dest path LCA index, right? Then we say LCA index plus plus, else break. Okay, so else we break, which means we find it. In fact, I think we can do it even better if we do this, and this is not, this is equal to, right? If it's equal to, then we will do this. We do this, and then D2J, and then we'll delete this thing, right? So this, and then if they're equal, we go plus plus. So now we can come out, we have the LCA index, right? We have the index pointing to the one that does not work. Oopsie doozy, we forgot one thing. Damn, we forgot the left and right. Now the start path, yeah, sorry, I forgot about the oh my goodness. That's okay, that's okay. So new int, bit like that, and 2, right? So we'll say this will equal to new int, right? New int, we got a path, and ooh, that's yeah, we need to do a path, and boolean is left. Was that bool is left? Yeah, is left. So path add current, I need to know if it's a left path coming to it. So we'll say here is left, right? If it's left, we go 1, otherwise we go 0. Okay. So the same here. So we'll do 2, and this will be a new int path.get. Wait, hold on. No. I have no idea what I was doing. Jesus. Oh my god, that's so bad. That was so bad. Okay, let me redo this. Redo this whole thing. This is all fine. All I need to do is do this. Okay. So the path is not integer. Okay, the path is not integer. It's this, right? So we shall add a new int, the node, and is left. If it is, if it's not, right? And then DFS go left shall be true, right? Go right shall be false. Okay, so now is missing type bool. Is that boolean? I was typing boolean earlier. Okay, so this is good, and DFS, it doesn't matter, we say true, because at the beginning it doesn't really matter. Okay, so now what we have is along the path with each node, if it's coming from a left or if it's coming from a right. Okay, so that's good. Now we have our LCA index, right? LCA index. And we can check the first one that is different. Now it's very important. Well, this is the first one that's different, right? So we need to know the first one that is the same. So we do LCA index minus minus. So this gives us the index that they're still the same, right? They're still the same. Okay. So now what we need to do is to see on the start, right? On the start path, how many more do we need? And we need to produce that many. So we need a string builder, right? String builder res equal to new string builder. Okay. And we need to know how many up we need to do, right? How many up we need to do. So we say for int I equal to LCA index I smaller than this dot start path dot length I plus plus, and we just say rest dot append a u, right? So if I have LCA index is here and I have start path length is, yeah, let's say in this case, right, so 0 and the path is 3, so there's 0, 1, 2, but we should only do 2, so I should say this is smaller than -1, right? So now we get a use. Okay, so we're up, and then from this again we need to get so we say for int I equal to actually LCA index plus 1 I smaller than this dot destination actually destination path, right? I plus 1. Okay, so we don't do the LCA itself, we do the next one, because the next one contains all the information that we need. And we say rest dot append. Now we're gonna say R or left, so we say this dot destination path I1 is equal to 1. If it is, it's going to be a left, otherwise it's going to be a right. Right? So we go this, so this is all the way to the land, and then we'll return this result. Okay, let's give it a shot. Hold a second, we have something that's wrong because we forgot the length. Okay, let's try it again. Oh, still not right because I forgot our toString. good. 736. Okay, let's just run the first. That looks good. We have 2 test cases. I'm actually gonna run a few more. Okay, these 2 are good. So I am going to run just based on this, right? So how about we say from 5 to 3, okay? Or from 2 to 4, right? Or from, 6 to 2. Or from 4 to 3. Okay, I think this is pretty much covers up everything. Yep, looks good. Okay, so I am going to... Wait, what the hell happened? Redo 13. Okay, is this LeetCode 2096. So first of all, find the path, right, from root to start value and dest value, recording also the passage of left or right branches. Then locate the lowest common ancestor of start and dest. We can use their path to quickly identify it. Finally, go through the path from LCA to start to identify the use, and go through the path from LCA to dest to identify the else or rs. Call it ON. I think everything is visited at most once. Okay, now we can submit this. Let's run one more test on this and then we're good to go. All right, let's try submit. It's pretty bad, 39 milliseconds. I wonder which part is slow. Maybe, I think the part that's slow is we have to go through the whole thing. Let's do this. If is no, or start path is not equal to no, and dest path, this dot dest path is not equal to no, so we can terminate this one early. So this dot okay, so we have an early termination. Let's see if it can make things a bit faster. Nope, it's the same. Okay, so I don't think that is the way forward. All right, let's check the solution. DFS, DFS, LCA plus DFS. So what you're saying is you can find LCA first. Oh, you have to find LCA first. Use the algorithm to find LCA. Okay, you find LCA, and then from LCA you do a BFS, right? You keep track of everything. So okay, let's see. Okay, the lowest common ancestor. Path to start, path. Now we find the path, find the path. Mm-hmm. Mm-hmm. Find path, directions. We dot extend times this. Extend. Yep, it's about alright. DFS optimized. Yeah, this is what I did. Yeah. Okay, that's not too bad. Find path. This is an early stoppage. So your DFS, Now we do it in one shot, and then we will check here. Yeah, I guess that's fine. Alright, that will be it for today. I need to go eat, and I'll see you guys tomorrow. Adios.